All right, so what we'll do today is talk about subjects. The first one of them is reasoning about Bayesian network classifiers. You can think of this as some kind of an extension of the discussion we did on sensitivity analysis, where we looked at the impact of the parameters on queries that we pose to Bayesian network models. In this part, we will also look, in a sense, at the impact of parameters, but on the classification query, because you can use Bayesian networks as classifiers. We'll explain this in a little bit, and then you can look at the impact of changing numbers on the classification ability of these networks. The second part, we will use the results from the first part to explain classifiers. That is, if you use the classifier and it makes a certain decision on an instance, it says this instance is positive or this instance is negative, you want to ask why. Why did you classify this as positive? And then we'll see how we can use the results from the first part to answer that particular class of questions. This material is not in your book. The first part is actually an old paper, has some substantial results, as you will see, and we'll give you the link to that. And the part about explaining classifiers is actually pretty recent, it's current work. We'll start initially by talking about the naive Bayes classifier, which is, you can think of it as perhaps the simplest type of Bayesian network classifiers, but yet a very common one. We've seen it before, at least we've talked about the naive Bayes structure. You have a node here that's known as the class variable, and you have a bunch of children which are known as the attributes or the features. And as you can see, this kind of a Bayesian network structure is quantified simply using a prior or a CPT over the class. In this case, we're going to assume the class is binary, so you have basically just two numbers. And then you have the CPTs that quantify the strength of each feature given the class, and we have three of them right there. So again, we've seen all of that before. The way you would use naive Bayes classifier is in a way as you would expect. You would have an instantiation over these features, like you see in this table here. We have three of them, and each one of them is binary, so we have 8 possible instantiations. We call these instances. And the idea is once you're given an instance, which is an instantiation of these guys, you compute the posterior on the class variable. That's done here. And then you have typically a certain threshold. In this case, let's say it's 90%, and you're checking whether the posterior is greater than or equal to that threshold. So we're tabulating all possible instances in this case, and what's the posterior. And if you look at whether that is greater than or equal to 90%, you see the answers here, yes, no. So the point here, as you can see, is I give you a particular instance, and the bottom line is you map that into a yes or no. And if you map the instance to a yes, we would say that this is a positive instance. If you map it into a no, then that's a negative instance. This is a special case, the naive Bayes classifier, of what people call generally a Bayesian network classifier. So in this case, you can have an arbitrary structure of a Bayesian network. It doesn't have to be naive Bayes. But then you have to designate a particular node C as the class variable, and then you have the set of attributes E1 through En. And as we talked about, an instantiation of these is called an instance, and you also have a probability threshold. And then you define the classifier like this. So E is an instance or an instantiation of these variables, and it is positive. You map it into 1 or yes, if and only if the probability of the class given E is greater than or equal to some threshold. Otherwise, you define it to be a negative instance. Today, we will mostly focus on the naive Bayes classifier because you'll see that we will be able to say a lot about it. But later, you'll see that the theme, the questions, and the direction we're going is not restricted to the naive Bayes classifier. So let me first, before we move on, give you a sense of what do we mean by reasoning about Bayesian network classifiers. What kind of questions we may want to answer about them. One of the simplest is I give you two classifiers, n and n prime, and they have the same structure, let's say, and you just change some of the numbers in one of them. And the question is, do I still have the same classifier? Right? If you're using the network as a classifier and you change number and the classifier doesn't change, then it doesn't matter. And as you'll see, changing these numbers could mean weakening or strengthening features, and that may be costly actually. And you may want to know, is it worth actually spending more money to get better features in some cases? Of course not if that does not change your classification ability. In fact, in some cases, if these guys disagree, if the two classifiers are not the same, you may want to know, where do they disagree? How many instances do they disagree on, and so on. And there is a whole variety of other questions that you can ask in this particular case. And the very last one will be explaining classifiers, which we'll focus on the second segment altogether. So here's the main insight behind what we will be doing. What you have is a box that has a model, probabilistic model, and you're doing probabilistic inference on it. And based on computing posteriors, you're making decisions, right? So there is a probabilistic model, there is probabilistic computations, but if you really look at this at a high level, what you're really doing is building what we call a symbolic decision function, because at the end of the day, the way you're using this is, I give you an instantiation of these three variables, and you're turning them into a yes-no. From a high level, this is a symbolic mapping. And what we will do is get our hands on that mapping and represent it in a symbolic way, away from numbers. And not only that, we will try to represent it using what we call a tractable representation, a representation that allows us to answer questions about it efficiently. And you've seen some of these representations before when we talk about circuits, right? DNNF, deterministic DNNF, and all of that. We'll bring those in to use in this particular case, right? So again, even though this is all probabilistic, what's really happening here is that we are specifying a symbolic mapping from features to a yes-no decision, and we're going to call this the decision function. And today what we will do is we are going to show how we can capture that symbolic decision function using a representation known as ordered decision diagrams, or ODDs. They look like this. We'll talk about them a little bit. And what we will see later is that if you adjust for notation, they happen to be a circuit type that you've seen before. So towards the end, in particular, in the second part, we will see how we can do more sophisticated reasoning on these guys to do explanations, right? So this guy captures the decision function that is synthesized by this Bayesian network classifier, in the sense that if you give me a particular instance like this, all you have to do is follow a simple procedure to render a yes or no decision. So in this case, I have that U is positive, B is negative, and S is negative. So you start at the top U. Since it is positive, you go this way, and B is negative, you go that way, and S is negative, you go that way. So this guy is saying that this instance is negative, right? What you will see is, we'll talk about a procedure that compiles this guy into that with the guarantee that they will make the same decisions. So in this case, you can see how simple it is to make a decision. You simply start at the top and just follow edges until you either reach a yes or no. In this case, we know how to make a decision. You compute the posterior and check against the threshold. Once more, guarantee they are equivalent. They will reach the exact same decisions, and we'll see the algorithm that will allow us to do this compilation. Okay, so here's another way of looking at it. This is our Bayesian network classifier, and what we have done here is tabulated all of the decisions that it can make by listing all possible instances and the corresponding decisions. And the bulk of this first part of the lecture is a compilation algorithm that maps the naive Bayes classifier into this symbolic representation. So the structure of our lecture will be like this. We'll tell you a little bit more about this guy, which is, we can do that in a couple of slides. It's very simple and intuitive, the ODD. It's a very famous representation, by the way, in computer science more broadly. And then what we will do is, we'll tell you a little bit more about the naive Bayes classifier, a number of very penetrating observations you have not seen before about how it behaves. Both of what we will say about OBDDs and what we will say about naive Bayes classifiers are of independent interest. Given how popular the naive Bayes classifier is and how prevalent, what you will learn about it is just useful on its own, regardless of what else we're going to do with it. But then we're going to utilize these observations that we're going to make about both to show you the compilation algorithm and also give you guarantees on its time and space complexity. All right, so here's a couple of slides on these creatures that are known as ordered decision diagrams. You can think of them like a generalization of decision trees. We know what a decision tree is. The difference in this case is these are graphs, not trees, in the sense that, as you can see, if I start here and I go this way, I come that way, I can still come to that node through another direction. That wouldn't happen in trees, right? In a tree, you will not have basically two parents for a node. And so in that sense, they generalize decision trees. And by the way, doing graphs versus trees can in principle lead to exponential reduction in size. If I allow you to have a graph, to have two paths come and meet back at the same node, that can significantly reduce the size. But actually, these creatures have a little bit more than that. The other property they have is that the variables are ordered in the sense that if you start from the top and follow any path to a leaf, you will encounter variables always in the same order, right? So you cannot, on one path, see x before y, and on another path, see y before x. And people say typically that the attributes are ordered in this particular way. So as you're going down a certain path, variable EI must come before EJ if you have that particular property. Let's see it again on this case. Look here. If you start at the top, and if you follow this path, x1, x2, x3, if you come down here, x1, x2, x3, right, x1, x2, x3. So regardless of what path you follow from the top to a leaf node, variables are always visited in the same order. This is a requirement. And it is because of this requirement that these guys end up being what we call tractable. Tractable means that you can answer questions about them efficiently, that you wouldn't be able to do otherwise. And because of this property, you get something that's known as the test once. Test once means that on any path from the root to the leaf, a variable is encountered only once. So you cannot be, here we're testing x1, right, to decide whether to go this way or that way. You can't later test x1 again, right? And this is the test once property. You can only check x1 or any variable only once on any path. That is implied by the fact that the variables are ordered. We will make mention of this property later as we will see on. By the way, I didn't explain this notation here, but the yellow means positive or high, and the dotted means negative. So in this case, we're assuming that the variable is binary. And in this case, these are really not known as ODDs. They're known as OBDDs, or ordered binary decision diagrams. So this is the more common type. And you will not see the term ODD that common. You will see this guy. But there is nothing that prohibits variables from being multi-valued. So you could have the variable x having the values high, low, and medium, for example. right? And you will have 3 edges coming out of it. And that's what we will use in this case. And those, we call them ODDs as opposed to OBDDs. The thing you need to remember is the variables must be ordered. And because of that ordering property, these guys end up being tractable. Let me give you an example of what does it mean to be tractable. Let's look at x1. So false, false. Sorry, this is true, right? x1 is true, x2 is true, x3 is true. Then true, true, true. We get 1. That instantiation is a model of this guy, correct? So that means this representation maps that variable instantiation into 1. If I ask you, how many variable instantiations are mapped into 1? Count them. This is something you can do on this guy in basically linear time. You can answer that kind of question easily. If I give you 2 of these guys and I tell you, are they equivalent? This is something that can be answered also efficiently. Do they represent the same classifier? Do they represent the same Boolean function? Because you can think of these represent Boolean functions, right? At the end of the day, they map every variable instantiation into a 0 or 1. That is a Boolean function, and so on, right? So all of these can be answered efficiently on these creatures. What we're going to do next is make a number of observations about the naive Bayes classifier. Before we talk about how we compile naive Bayes classifiers into these guys. Here's the naive Bayes classifier. The observations that we will be making will be based on the following. We already know this. That's the kind of characteristic equation that says if you have an instance E, which is an instantiation of these guys, and you want to know whether it's a positive or negative instance, you compute this posterior and check against the threshold, right? In that case, that's when we would map this to 1. Now, what we're going to do is, and you're going to see the value of it, instead of doing this, we're going to work in the space of log odds. So, instead of doing this test, which is the conditional probability C given E, greater than that, we're going to look at the log odds of C given E. So basically, you're looking at C given E and divided by C prime given E, and taking the log of that. And similarly here, and then you get this equation. So now what you want to test is whether this guy is greater than or equal to that row. Remember the symbol here because it's going to play a key role as we go on. The main observation in the next few slides are all going to be centered on the following interesting questions, which will play a key role in both designing our algorithm and analyzing its efficiency. The observation is the following. If I give you a naive Bayes classifier like this, which as we realized represents some kind of a decision function, symbolic decision function, and if all I do is change the prior, this table, on the class variable, I just make modifications to it, would I change the symbolic decision function? So if you take this guy now, 87%, right? And you make it 90%, does that change the classifier? Would the old guy and the new guy end up doing anything differently? That's the question we're going to focus on. And the gist of it, what you're going to find is the following. We're going to find that if this is 87%, there is an interval that this belongs to. And as long as your prior is in that interval, this thing doesn't change. It will end up leading to the same classifier. And you'll see the implications of that observation. And we'll characterize that interval precisely. But along the way of doing this, you learn a lot about naive Bayes classifiers that are useful anyways. Okay? But then that's the key result, and you'll see how we're going to exploit it in multiple ways. And we're going to start with the following. Okay. What we're doing here is looking at the basic equation of the naive Bayes classifier, which is if you want to classify an instance, as we discussed, you're going to compute this guy, correct? And you're going to check whether this is greater than or equal to this row. And what this is doing is just fleshing it out. This guy is that. If you use Bayes' rule and invert this. So instead of C given E, you do E given C. You can write the first part like this. And the bottom part similarly like that. What happened here is C given E becomes E given C multiplied by the probability of C divided by the probability of E. And as we know, in a naive Bayes classifier, the attributes are independent given the class. So you can break this into a product and look what you get. These guys cancel, and now you have a log. So because of the log, you can break this into its own component. You get this, and this guy into its own component, and you get that. Look at the beautiful form that we now are getting. What is this guy? This is just the prior. And look what we did here, a sum over all features, and for each feature, look what we're doing. Probability that that feature will come out the way it came given the class is on and given the class is off. This guy here, we're going to use W E sub I as a notation, and look this final form. Oh, you will be surprised by how many applications we're going to get to see now. What is this? This is the posterior log odds, correct? That's what I'm going to use to do the classification. And this guy says it's simply the prior log odds and a summation where every one of these guys is, you can think of it as the weight contributed by each feature. Okay, stare at this again. This is the posterior that I'm going to use to do the classification. And it's an addition of this and that. When I change the prior on a naive Bayes classifier, I'm only changing this guy. This guy is fixed. All right? You will see in the literature many properties about naive Bayes classifiers, sometimes stated as theorems. And if you look at this equation, you're going to see why they hold. But we're going to visualize this in a little bit. Again, remember what we're trying to do is finding equivalent naive Bayes classifiers that result from only changing the prior and trying to capitalize on that later. Which is this question. If we change the CPT of the class variable C, thereby changing the prior log odds from this to that, will we still have the same classifier? Okay, another quick derivation, and then we'll visualize this, and you guys will see the answer. So this is before we made the change. This is the equation we just derived, that the log odds, the posterior, is just the prior plus a bunch of weights. Each feature contributes a weight. We're good? This is what happened after we made the change. This is the posterior, correct? And this is the changed prior. This doesn't change. The contributions from each feature doesn't change. Let's take the difference. This minus that. What happens? These guys cancel, and look what you get. This difference is that difference, and let's call that delta. You're going to see delta next on the next slide. So in this space, in the log odds, the beauty of it is if you're making a change to the prior, it will be exactly the change that you will see in the posterior log odds. The next slide, I'll show you a visualization. And this visualization will be the basis of an equation. The equation would look nasty. But it's not, once you understand the visualization. And that equation is the one that characterizes this interval for the prior. That if you keep your prior of a naive Bayes within that interval, you will not be changing it. The symbolic decision function will be as is. Okay? This is kind of like the key punchline of what's going to happen today. Okay. Look at this. What's happening here? Oh, the top two equations are just reminding us of the fact that we look at the log odds and then compare against this guy. That's when we classify this as a negative instance, and we would classify it as a positive instance if this guy is greater than or equal. So in this case, we have 8 instances. So suppose you have basically 3 features. They're binary, so there are 8 instances. And what we're doing on this line is we're laying them out depending on this quantity. Okay? So for each instance, you go ahead and compute this quantity, which is the one you're going to use to decide whether that instance is positive or negative, right? And you lay them out. And what is this? This is our threshold, rho. So according to our criteria, if this guy is less than rho, then it's a negative instance, correct? If it's greater than or equal, it's a positive instance. So we have 4 negative instances, 4 positive. We're good so far? Okay. Now, what happens when I change the prior? As you see in the previous equation, when I change from this to that, what did I change? From this to that. What happens to this picture? What am I doing? I'm basically shifting these instances left or right, depending on whether I increased or decreased. So in this case, I made a change of delta 1, right? So I increased this guy by delta 1. What happened to these guys? They shifted all the way that. Okay, look what happened here. This guy is still below rho. Did that change the classifier? No. All of the negative instances are still negative. All of the positive instances are still positive, right? Okay, if I shifted a little bit more, now this is sitting at rho. What happened? I changed the classifier. And what is the change? This instance used to be negative. Now it is positive. You guys see that? Okay, let's try to do the shifting the other way around. Now I shifted by delta 3. So I shifted things this way. Did I change the classifier? No. These are positive. They're all still positive. These were negative. They're all still negative. Same classifier. If I shifted a little bit more, then I did change the classifier. Why? This guy used to be positive. Now it's negative. Okay, you guys see what's going on. I have a certain amount of shifting that I can do, left or right. And if I stay within that, the classifier stays exactly the same. And what's the key to this shifting? Look at the top. These two instances are the key to defining the amount of shifting I can do. Think of this as the highest negative instance. Think of this as the lowest positive instance. If I got my hands on these two guys, then I can identify the amount of leeway that I have. The other thing that I want you to see, because that's going to play a number of roles later, is the fact that the distance between these instances is basically fixed. We're just moving them, shifting them left or right by changing the prior on that class variable. Okay. A little bit more visualization before I give you the equation, which is the central result here. So here's a naive Bayes classifier over these guys. The prior is 87. You go ahead and change it to 95, and you keep everything else the same. That is, the CPTs for these features are the same, and then you ask the question is, are these two classifiers the same? That means, do they induce the same decision function, symbolic decision function? What we're going to do is, we're going to define for this guy what we call the equivalence interval of this class variable. And for this guy, it happens to be this, as you will see. That as long as the prior is here, then this guy is the same. So we will say they're equivalent if the prior of this guy belongs to that interval, right? And we're going to call this interval this. Okay, so here's what we're going to do next. I will show you the equation for this guy. And you will roughly get to see why it works because of what we did. And then we're going to end up showing you how we're going to use it during the compilation process later. We'll also do one more observations on naive Bayes before we get into the compilation algorithm. Guys, are ready for the equation? Okay, it's friendlier than it looks. Let's parse through this. We're talking about an interval, right? And it says this interval is made of these x's. So far, so good? And I'm going to describe these x's for you. These are x's where x over 1 minus x equals that. That's the description. We know what this is. It's easy, right? This is the prior. We know what this is, right? This is the threshold. So the only thing that's left is y. And y happens to be this interval. And you'll see that this is friendlier than you think. So if you have this interval and y belongs to this, then you plug all possible values of y here, and then you get that guy. So let's look at, so it's really simple once you understand this. What is going on here? Look at this guy. What are we doing? I'm looking at the posterior, C given E, and I'm trying to find the E, the instance E, the positive instance E, right? That minimize this quantity. We've seen that before, right? This is the lowest positive instance. And what am I doing here? I'm looking at C given E, and I'm searching for the instance E that is negative, that maximizes that. So let's look at our visualization. This guy is this. Talking about this guy. And the other guy is that. Makes more sense now. Of course, there's a little bit math behind this, but you can see what's going on here. Why these two particular instances play the role in defining the equivalence interval of the classifier, right? Because they define the amount of left and right shifting that you can do while keeping the classifier as is. Stated more formally is the theorem 1, given a naive Bayes classifier, two of them, Fn and Fn prime, that differ only in the prior and the class variable, then they are equivalent if the prior of one of them belongs to the equivalence interval of the other, and that's the equivalence interval. One more observation, since we've made this investment and now you understand this picture about how the instances are laid out, let's utilize that visualization to make one more observation about naive Bayes classifiers, and that will lead us to something called theorem 2, and you'll see how the two theorems will play a role in understanding our compilation algorithm. And by the way, our compilation algorithm will be very intuitive, few slides, once we have all of this. Now, if I give you features, n features, let's say binary, how many instances do you have to the n, correct? This is the number of instances. Let's call that number of instances now m. So now you have m instances, correct? How many classifiers can you build over these m instances? In general, to the m, correct? Why? Because every time you choose a subset of these and call them positive and the remaining are negative, you have a classifier, a distinct classifier, correct? So it's really how many subsets do you have out of the features? This is in general. But the question is, now we're talking about something more specific. I'm talking about a naive Bayes classifier, and I'm talking about changing the prior on the class variable. How many distinct classifiers can I actually build? The idea is, if I have a naive Bayes classifier, and the only change I'm making to it is changing the prior on the class variable, what happens when I change the prior? I'm shifting these instances either left or right, correct? As long as this row remains in between these two guys, then I have not changed it, right? If I shift all the way until this row ends up sitting between these two guys, then I have a new classifier. And there again, I have a certain amount of shifting where it's still the same classifier and so on. So how many distinct classifiers depends on how many places I can take that guy. Now you said it's m. M is the number of instances. It's actually m plus 1. So these are 8 guys. If you really count 1, 2, 3, they're 9. Interesting. Arbitrary 2 to the m, in this case m plus 1, and that's basically what this theorem 2 is saying. The number of distinct naive Bayes classifiers, including the current classifier, that can be induced by changing only the prior of the class variable C is at most the number of instances plus 1. We use this to refer to the number of instantiations, right, which is the number of instances. Two key observations about the naive Bayes classifiers, and they're both easily seen once you look at the log odd space and this picture. And as I said, both of these theorems will be crucial for us. In the next few slides, we're going to talk about converting naive Bayes classifiers into ordered decision diagrams. And we're going to find that theorem 1 will help us save space and time when doing the compilation, by sharing sub-ODDs and therefore getting a graph structure instead of a tree structure. And theorem 2 will help us see the bound on the size of the resulting ODD. You guys are ready for the algorithm? Here's how it's going to work. What you have is these features. And what we really do is, in a way, what people call it some kind of a depth first search on these features. You take U and say, let's assume that it's positive. Let's assume it's negative. And when U is positive, you take V and say, let's say positive, negative. And so you build what people call a decision tree, effectively. Except that, look what we're going to do. If you do that, start with U, let's say it's positive, and then I'm saying now V, it's negative. I'm here, correct? So now S, positive, okay, but let's say I'm here at S. What happened so far? Up until this point. I fixed the value of U and B, correct? Okay. Visualize this on the naive Bayes classifier side. What I've done really is I fixed the value of this guy and I fixed the value of that guy, correct? And then I computed the posterior over this, correct? Remove these guys. What did you really have now? You just have a smaller naive Bayes classifier that has only one feature and has a new prior. You guys see that? What happens when I go down the other path? I'm here. I did negative, positive, different instantiation. Right? What happened? Same story. Okay. Now you guys are going to get to your biggest reward. See what's going to happen now? What I'm doing, if I continue the compilation process, I'm really compiling this classifier into an OBDD, right? And if I continue down this, I'm compiling this guy into an ODD, correct? But these guys are exactly the same. The only difference between them is the prior on the class variable, correct? If they happen to be equivalent, then these two guys are the same. And I can make them point to the same thing. And that's what I want to do. And that's how you get a graph instead of a tree. And I think in this case, in fact, they do end up being equivalent. So naive Bayes classifiers differ only in the prior of P. The classifiers are equivalent if and only if the prior of P belongs to the interval, equivalence interval of that. And in that case, they are. And look what happens. It is this notion of an equivalence interval that allows you to compile a graph instead of a tree. And the idea is you do this tree search, but every node in the tree, in a sense, corresponds to a new partial classifier. So this is now a partial state of this algorithm. By the way, as we said, we have to have an order of the attributes. So in this case, we're using that particular order. So I went and built these things. I'll tell you how these guys are computed. But this point, okay, this is the state of the algorithm. And for each one of these, I have the equivalence interval. Because remember, each one of these corresponds to some kind of an naive Bayes classifier, and that's the equivalence interval. Okay, so now I'm here. This is the state of the algorithm. And the minute I set U to this, that's the posterior. And what do I do now? I have to see whether I already have, at this point, this is a classifier over what? Over the remaining attributes, B and S. So I want to see, do I have another one over B and S where this belongs to their equivalence interval? The only one I have is this. That is over these two, and it doesn't, right? So this does not belong to that. So I have to keep going in this case. And now I try to set B to positive. So now what's going on? Negative, positive, and that's the new posterior. So what do I have to do? Do I have already a classifier over S whose interval, equivalence interval contain this? I do, correct? That's this guy. What does that mean? Done. I just point to it. I don't need to keep going. And then I try negative. And the posterior in this case is that. And it happens to also belong to this equivalence interval. So again, I just point to it. You guys see what's going on? So you're doing this tree, but you don't have to always extend it. Sometimes you stop and you say, wait a minute. I got to a point where I've already compiled a classifier for what I need to compile next. I just point to it. Now, it turns out that you can compute the interval for a node from the child intervals. So for this guy, given that I have this, I can compute the interval for it. For this guy, this can be computed from this and that. The formula is in the paper. We'll give you a link to the paper on this. So these can be computed incrementally as you're doing the compilation algorithm. Now, one thing you've seen this example before. That's the one we started with, but it doesn't look as hairy as this one. Why? We can reduce it. Exactly. If you look at B is redundant. It's saying that whether it's positive or negative, I'm going to always go that way. So you really don't need this guy. You can just take U directly to S. And S is also redundant in this case. I don't need it, and I can take B directly to true, correct? If you remove these guys, you get the guy we've seen at the very beginning. Good? Very nice. Very nice. You will maybe appreciate this even more if you knew more about OBDDs or ODDs. I gave you a hint. I told you they're tractable. But they are perhaps among the most tractable representations of Boolean functions. Some people claim that OBDDs are the most studied tractable representations of Boolean function in computer science. The amount of things you can do with them efficiently is just so amazing, which makes this particularly interesting. So if you manage to compile your classifier into an OBDD, you're in heaven as far as answering questions. I'll give you some examples in a little bit about what you can do with this. In fact, we're almost done with the first segment. But then we'll even exploit it more aggressively when we get to the second part about explanations. And the second part about explanations will be relatively short, by the way. The bottom line is you can easily get a tree that is exponential in the number of features, but using these you can show a bound that is n over 2. N over 2 in the exponent is significant. Let's just take an example. 50 features binary. This is 2 to the n. And you splash this by half, it becomes feasible, right? So it's a big deal. The actual sizes are much better than this. In fact, I'll show you just quickly. We're almost done with this part, a few minutes. I'll show you some experimental results from naive-based classifiers that are from UCI machine learning repository, and the threshold here was used half. You have to realize also the size of the OBD depends on the order that was used, so different things were tried as far as how to order the variables. And here's the sense of what's going on. So this is the number of attributes, but these are not binary. You gotta be careful here, right? So this is way larger than it looks. This is the actual number of instances. So like even though this has 22 instances, 22 features, that's the number of instances. The bound says this is the actual size of the OBDD, and you can see the difference. Most operations on OBDDs are linear or quadratic, so this is actually very practical. Let me just now show you a couple of things you can do. Remember, how did we start this segment? We started by talking about reasoning about classifiers. That if I take the naive-based classifier or the numeric classifier and I compile it into a symbolic one and a tractable one, then I can start answering all kind of questions about it. One of the simplest questions is, I made an arbitrary change to the CPTs. Does that change the classifier? That you could easily handle by compiling each one of them into an OBDD or an ODD. Testing the equivalence of two ODDs can be done very efficiently. So you have one classifier and another, and they have different numbers. You compile both and you check equivalence. Easy. If they're not equivalent, you want to know where do they disagree. Easy. So the classifiers, both of them are at your fingertip. But here's a couple more things you can do. Someone comes to this guy and say, well, currently the false negative is this, the false positive is that. I'm gonna sell you a better unit test. Right? Should you buy it? And in this case, if you just changed it to a false negative of 10 and 5, you will not be changing the classifier. Don't pay money for that guy. Right? What was it? 2710? That's substantial. 10 and 5. You see that? That's a lot. You would probably pay for this if you didn't take this class. Now don't. You go check this guy, right? Compile and see, and says same decisions. Guaranteed. And if you go down to 5 and 2.5, then you will get differences. And as I said, you can even characterize those situations where they're disagreeing. So you can characterize the situation. You can do all kind of things like compute their likelihood, analyze their properties, and so on. Okay, here's another example. Someone says, I want to sell you an additional test. So instead of 3, you have 4. Right? Is this going to help? Now, what does that mean? That means there is an instance of these 3 variables, where depending on the value of this, you will do something different. So it's refining your classification. And you want to ask, does it really? Does it? Is there any instance over these guys where this will make a difference, will make me change my mind or decide this way or that way depending on that? You can also check that. And in this case, same decisions if this, but not if that. So pretty powerful, pretty powerful. You guys see what happened here? We abstracted away from numbers to decisions and start doing the analysis at the symbolic level. These are detailed creatures because of the numbers and because of we learn these numbers from data, At the end of the day, we use them as symbolic functions. This is the dilemma that now currently AI has. They started by symbolic representations. They thought the whole game can be symbolic. And they thought this is not enough. It's too abstract, too coarse. We've seen that in the first lecture. And then they went to numbers. That was good, data. But then they got creatures, and then what they end up doing with them is they use them symbolically. They use them to induce symbolic functions. And now in AI, people say, wait a minute, why did your classifier do this? Explain. Now you have real-world applications. There is accountability. How do you explain? These creatures are so detailed, but they're doing something symbolic. If you want to explain, what do you want to do now? You want to reason symbolically. Now we're going to go back to all of the techniques that we invested decades in. At some point we stopped training people in. They're coming back. You've been exposed to them. OBDDs is one of them. You basically need the combination to be able to be effective in this particular case. So what we did is we went to the numeric world. We went to the machine learning and the numbers and learned the right classifier, then abstracted it and compiled it symbolically, used symbolic techniques, and then I'm now reasoning about your AI systems. So this whole new theme, this whole new direction of reasoning about AI systems under which you get explainability, and now people talk about fairness and other aspects of AI systems, you basically need to employ symbolic techniques. So we'll show you next. Let me see. Okay, just the conclusion. We'll take our 10-minute break, and then we will capitalize on this investment even more in the next part. What we will do is, now that you have the symbolic decision function expressed in tractable form, we're going to show you how you can easily now start doing things like, why did the classifier classify this positively or negatively? And you're going to see that's all going to be symbolic. In fact, you've seen some of the stuff before. 10-minute break, and we get to explaining classifiers.